All right, welcome back. Another section of our fun pre-calculus course. All right, so this section starts getting into functions. Now, functions and function notation can be a little bit tricky until you get the hang of it, but we'll see if we can try to make it a little less confusing. All right, we have introduction to functions and function notation. In general, two quantities that are related to each other by some rule of correspondence, i.e. an equation, is called a relation. So in an equation, usually you have x and y, and sometimes you have other variables, but x and y are related to each other by some way, by some manipulation of one to get to the other. That is a relation. But we can go even further with that. However, if the value of one quantity is determined by the value of another quantity, then in mathematics we have a function. So one quantity helps determine the other one. More specifically, if a variable y is determined by a variable x, then y is a function of x. So in this specific case, we're saying that y is determined by x. Now there's other times that x might determine y might determine x. So it depends. But in this specific instance, I'm saying that x helps determine the value of y. And we'll dig more into that in a second. So now, first example, determine if a is a function of b. So a helps determine, is determined by b. B is a function of a. So b is determined by a. Both or neither. So if a is the radius of any US coin and b is its circumference, which one of these do we have occurring? So is a function of b? Is a determined by b? Or is b determined by a? Or both or neither? Now, you should say that the circumference is determined by the radius, right? If we know the radius, we can get the circumference because we know c equals 2 pi r. So if we have the radius, we can get to the circumference. So we know that this is happening. But is that the only thing that's happening? What if I rearrange this formula and I divided both sides by 2 pi? If I divided both sides by 2 pi, now r is determined by c. So now this is happening. So the answer for this one is both. Both. We can write it either way. So it depends on how it's written to determine if one determines the other. So, I know, trick question. All right, let's take a look at the technical definition for a function. A function f from set A to a set B is a relation, so that correspondence, that assigns to each element x in the set A exactly one element y in the set B. So, one value of x, one value of y. The set A is called the domain, or the set of inputs of the function f, and the set B contains the range, or the set of outputs. So domain is the inputs, range is the outputs. So characteristics, so here's the important parts. Each element of A must be matched with an element of B. So you can't have an element of A just hanging around by itself. It's got to have a partner. 2, some elements in B may not be matched with any element in A. So that's kind of the opposite of number 1. Everybody in A has to have a partner, but everybody in B might not. So that's okay. 3, 2 or more elements in A may be matched with the same element in B. So so you have 2 elements in A saying, oh, I like this same partner in B. So that's okay though. But 4 says an element in A, the domain, cannot be matched with two different elements in B. So B can be promiscuous and have two partners in A, but not the other way around. So A can't have two partners in B or more. I know, it's kind of weird how that works, but that's the way it is. We're going to see some other ways to analyze functions later on, so don't get too bogged down with this technical definition and stuff. But let's take a look at an example and see if it helps illuminate these 4 conditions. So we have a set A that has 4 numbers in it, 0 through 3. We have set B that has 5 numbers in it, -2 through +2, all counting numbers, all integers. So now let's take a look at our partnerships that we have and see if they're okay. So 0 and 1, so we had 0 is mapped to 1. We got 1 to -2, so 1 to -2, 2 to 0, so 2 to 0, and then 3 to 2. So are all 4 of these conditions met? Each element A must be matched with an element of B. So all 4 of our elements in A have to have a partner. So 0 does, 1 does, 2 does, 3 does. Ding. So 2, some elements in B may not be matched with an element in A. Well, there's 4 ordered pairs, there's 5 numbers in B, so somebody's missing out. Which one is it? It looks like -1 doesn't have a partner, but that's okay. So that's good. 3, 2 or more elements in A may be matched with the same element in B. Well, we don't have any element of B repeated anywhere, so that's okay. So we're not breaking any rules, so that's fine. 4, an element of A cannot be matched with 2 different elements in B. So is any element of A matched with 2 elements of B? And each one's only used once. So we're good. So this one is, yes, all 4 characteristics met. All right. So that one is good. B, so we got all the elements of A have to be matched. So 0, 2, 1, 3, 1. Okay, so 1 is happening twice, so we're going to have to keep an eye on that one. It's being promiscuous. So we got, and all of these are in B, the second coordinate. -1, 2, -2, 0, and 1. So we're good. So all the elements in A are matched with an element in B. So that's satisfied. Some elements in B may not be matched, but that looks like it's not applied here because all of them do have a partner. Number 3, 2 or more elements in A may be matched with the same element in B. All right, so we don't have, do we have that? 2 elements in A may be matched with the same element in B. And I'm not seeing that all these are used. I mean, this element's used twice, but not the way that it's referenced in 3. So I think we're okay with that one. But what about 4? An element in A cannot be matched with 2 different elements in B. There's the rub. So the same element is matched to 2 different elements in B. That's no good. So this would be a no. Number 4 is not met. So, all right, so that one failed. It's not a function. From A to B at least. Okay, what about this one? This one's unique. So we got all the elements in A are there, but they're all mapped to 0. So is that okay? Well, remember, so we have 1 is satisfied, 2 is okay, 3 is okay because that's what's happening here. The two or more elements in A may be matched to the same element in B. So they're all mapped to one element in B, but that's okay. 0 is a promiscuous partner in this case. And then 4 is not being broken either. So this would be a yes. All 4 are met. All right, what about this last one? 0 to 2, 3 to 0, and 1 to 1. So what's the problem here? It's the very first one, yeah. Each element in A must be mapped with and matched with an element of B. And we're missing one. We're missing number 2. 2 is not matched in to anybody. So no. Number 1 is not met. So that's kind of the idea when you have a discrete set of numbers and that you're dealing with and trying to represent functions. We're going to see how we can generalize that even more so soon. But let's take a look at some more terminology that hopefully rings a bell for you. So within relations and functions, the variable corresponding to the first coordinate is the independent variable, and the variable for the second coordinate is the dependent variable. Thus, if we use an equation in two variables to represent the function, i.e. y is a function of x, then x is the independent variable and y is the dependent variable. So again, x is determining what y is. Y is determined or dependent upon what x is. That's the way you have to think of it. So let's take a look at the next page. And we'll tackle this one. If a relation is described by an equation, i.e. y equals 3x plus 1, then it can be determined to be a function either algebraically or graphically. Graphically, we will see in the next section. Darn. So you probably remember how we can check graphically, but we'll get to that very soon. Algebraically is a little bit more interesting, but we have to first look at how they want you to determine your function. So in this case, they want y as a function of x. So y is dependent upon x. So the only way we can really see algebraically, excuse me, is to get this in terms of y. Because you want to see what y depends on for it to be created. So we have to get y by itself. So this one we can do pretty quickly if we move the 9 over to the other side and add 9. And then if we divide by 3, and I'm going to flip-flop the sides, so y is going to be equal to x plus 9 all over 3. Now if you wanted to make that into an equation, like a line equation, you could do it like that. I would take either one in this case. But what is this telling you? So if you wanted to make sure all those characteristics are met, whatever value you plug in for x, you're going to get a value of y. You're going to get a partner of some sort. So that first condition is met. Every value you can think of for x is going to have a partner in y. So that's satisfied. Number 2, which I've already forgotten. So let me scroll back here. Some of the elements in B may not be matched with any element in A. So are there going to be any values for y that doesn't have a partner in x? No, so that one's kind of ridiculous. X can be matched with more than one value of x can be matched with the same partner in y. Okay, that's not going to apply here, but it might with a different equation. But the last condition is the most important one. Is x being matched to more than one value of y? Is x being promiscuous? And the answer is no. If there's only one value of y you're going to get for every one value of x. That's really the critical condition when you're looking at functions, y as a function of x. So the answer to this one would be yes. And the answer is because one value of x yields one value of y. That's the critical reason why. Let's see what happens with the next one. Y squared equals x squared. Pretty simple equation, but we still want to know what happens with y. What is y determined by? Now in this case, if we take the square root of both sides, we get y, and technically we do get a negative y. The negative we're not so much worried about. It's really just the positive, because one will usually take care of the other one. So we'll just kind of ignore this one. But what is y equal to? We got to take the square root of x squared. Now technically, is it just equal to x? No. Remember, when you're taking the square root of something, you usually get two results. So technically we would get a positive or a negative value of x. So y is determined by two values of x. Or excuse me, I should say it the other way around. One value of x is going to yield two values of y. So when I plug in x equal to 1, for example, I'm going to get y equal to negative 1 and y is equal to positive 1. I get two values of y for that one value of x, and that is no good. So this would be no, because one value of x yields two values of y, and that's no good. So that's how we can do this algebraically. A little bit confusing, but the big thing is you want to see if there's multiple values of y when you get y alone. And this happens here. It doesn't happen here. So, all right, let's stop there, and then we'll pick up some more problems in the next video. See you soon.